are going to discuss resistance. I think all of you know about the resistance. I want to discuss the important points which are very useful for exams. Okay, so resistance, we know very well which opposes the flow of current is nothing but resistance, which opposes the flow of current. The current is flowing, it will be opposes that one. Okay, for example, here it is a resistor symbol and we denote with the letter R. If the current is flowing, then this resistor opposes the flow of current. Okay, so resistance is nothing but which opposes the flow of current. It is a property of the material which opposes the flow of current. Okay, here this resistance is generally depends on physical quantities. Depends on physical quantity like length and area. Okay, how it will be depends upon this resistance is directly proportional to length of the wire. That means if the length of the wire is more, the resistance also high. Second one, resistance is inversely proportional to area of the conductor. So from this one, we can say that R proportional to L by A. R proportional to L by A. If the length increases, resistance increases. If the area increases, resistance is decreases. Okay. So that means you can understand this one. For example, if the area of the cross section is like this. Okay. If here the area of the cross section is like this, in case of B conductor, here for example, if you can consider it is a small road, okay, a very narrow road, then what is happening? All the vehicles moving slowly. Moving slowly means less current. Less current means you can say higher the opposition, that is higher the resistance. So that means lower the area, higher the resistance. All of you getting my point? Here area is less, there is a lot of opposition is there. Okay, to flow the electrons may not flow easily. So may not flow means less current. So area of the conductor is less, resistance is more. For example, if the road is wide, four-way line, okay, if you can consider, then the vehicles can move very fastly. That means less opposition. So higher the area is lesser the resistance, more current. Okay, that is the understanding we can say. So if you remove the proportionality, we have to take one constant now. That constant is equal to rho L by A. So that means resistance is depends on resistivity, length and area. Here rho is nothing but you can say a resistivity or specific resistance. We will discuss in detail about this, don't worry. Specific resistance. Okay, so up to now resistance is depends upon the physical quantities like length and area, that is R is equal to rho L by A. Very important one, friends, very important one. And this resistance also depends on temperature. Resistance also depends on temperature. How it will be depends on temperature? That is based on the coefficient of temperature, that is coefficient of temperature, that is nothing but alpha. Okay, so how it will be depends on temperature? In case of conductors, as the temperature increases, the resistance also increases. Okay, as the resistance increases, as the temperature increases, resistance also increases. How it will be? Let us understand this one. Okay, up to now all of you clear? I think R proportional to L by A and R is equal to rho L by A. It also depends upon the temperature. So here actually we have the temperature coefficient of temperature, that is nothing but we can say alpha. Alpha is equal to RT minus R naught by R naught into T. R naught is nothing but resistance at 0 degree centigrade. Resistance at 0 degree centigrade. RT is nothing but resistance at T degree centigrade. Okay, and T is the temperature. Okay, T is the temperature. Then alpha is nothing but RT minus R naught by R naught into T. It is a very important formula, friends. You can say it is a temperature coefficient of resistance. Of resistance. Okay, this if the alpha is RT minus R naught by R naught into T, if you multiply this one, then you are getting RT minus R naught is equal to alpha into R naught into T. Alpha into R naught into T. That means you can say that the change in temperature is directly proportional to the resistance at 0 degree centigrade into that temperature. Okay, so from this you can say RT is equal to, if you send R naught to this side, if you common R naught, then you are getting 1 plus alpha T. Okay, here if the alpha is positive, if the alpha is positive, for example, it is a positive value, then you will get 1 plus something positive value. So more than 1. More than 1 means RT is higher. So if the alpha is positive, RT is greater than R naught. That means from this understanding, we can say that resistance at T degree centigrade is greater than 0 degree centigrade, means here as the temperature is high, resistance also high. Okay, so we can say in case of conductors having positive alpha, that means positive temperature coefficient of resistance. So that's why, so as temperature increases, the resistance also increases. Okay, but in case of semiconductors, it is just opposite. It is just opposite. So from this, as temperature increases, resistance increases. As the resistance increases, current will be decreases. Okay, so that means in case of conductors, if you increase the temperature, the current is going to be decreased. Now coming to semiconductors. Okay, so in case of semiconductors, the alpha value is negative. If the alpha value is negative, then what about RT? RT is equal to R naught into 1 plus alpha T. If this value is negative, this total value is negative, this total alpha into T value is negative, then you can get 1 minus something. 1 minus something means we are getting RT is less than R naught. So that means from this understanding, we can say that same as in case of semiconductor, as temperature increases, resistance will be decreases. Okay, that means these are nothing but we can say negative temperature coefficient of resistance, and these conductors are nothing but we can say positive temperature coefficient of resistance. Okay, I think all of you got it. So once again, coming to the temperature coefficient of resistance, it is alpha. Alpha is equal to change in resistance by resistance at 0 degree centigrade into the temperature. Okay, so if you summarize this one, you will get resistance at T, any of the degree centigrade, or T of degree centigrade is nothing but 0 into 1 plus, that means resistance at 0 degree centigrade into 1 plus alpha into T. Okay, and conductors, in case of conductors, those are positive temperature coefficient, so that's why directly proportional. Here negative temperature coefficient, so that's why you can say inversely proportional. Okay, inversely proportional. In this way, the temperature, the resistance will be depends upon the temperature. And we know very well, coming to the units of resistance. Units of resistance. To recognize the scientist ohm, the units are ohms, and we know very well the symbol is like this. The symbol is like this. Okay, so this resistance is depends upon resistivity, length and area, and also temperature. And how it will be depends upon temperature, depends upon the alpha. Okay, different for conductors and different for semiconductors. Okay, and now after this one we have to discuss about the resistivity. We have to discuss about the resistivity. Okay, so coming to the resistivity or specific resistance. Specific resistance. Okay, resistivity or specific resistance is denoted by the letter rho, and this rho value, it is the property of the entire material. It depends upon nature of material. It depends on nature of material. Okay, it does not depend on physical quantities. Does not depends on physical quantities. What are the physical quantities? Like length, area and value. What is mean of these 2 points? Here it depends on nature of material means, depends on nature of material means, if the silver, it has a silver, it has the one resistivity. For entire silver material, the silver may be having 1 meter length, it has the same resistivity. It has 1 kilometer length also, it has same resistivity. So if you change the length from low to high or high to low, whatever it may be. For example, if you cut the length of wire into 2, each that is, for example, if the length of the wire having the resistivity rho, if you cut into 2 parts, then each part having resistivity rho only. If you cut 4 parts, then each part having resistivity rho only. Or if you add the same type of material also, the resistivity is rho only. I think all of you getting my point. If you not getting my point, you have the facility, that is, you can watch it again. Okay, so that is the facility in case of this recording videos. Okay, so I want to say that it not depends upon the length of the wire. Okay, so whatever it may be the length, 1 meter or 1 kilometer or 1000 kilometer, if it belongs to same material, same resistivity. If it has aluminum, same resistivity. Okay, it has some fixed value. If it is a copper, it has some fixed value, like that. Okay, so it does not depend upon the physical quantities. It depends on only the nature of material or type of material and also the temperature. You can say and temperature. Okay, so it not depend upon the physical quantities. If you that means if you cut into 2 parts, 3 parts, 5 parts, or if you have the same material, different length and different cross sectional area, then the resistivity ratio is 1:1. 1:1 only. Okay, all of you getting my point. Based on this, we are getting so many questions are framed. Okay, so it is very, very important. And one more thing is nothing but you can say the units. Coming to the units. So coming to the units of this one, if you want to find out the units are generally, there is nothing but ohm, meter. Okay, so to find out, we know very well R is equal to rho L by A. So from this, rho is equal to R into A by L. Okay, so that means resistance units ohms, area meter square, length meter. So meter get cancelled out, you are getting ohm meter. So ohm meter is the unit of resistivity or specific resistance. Okay, and coming to the resistivity values, the typical values, these are also sometimes important. The resistivity values in case of conductors, Okay, all of you note it. These are very, very important. Generally, 10 power minus 8 ohm meter to 10 power minus 3 ohm meter. Okay, and in case of semiconductors 10 power minus 3 ohm meter to 10 power 6 ohm meter. In case of insulators, more than 10 power 16, more than 10 power 16. That means generally the range is 10 power 6 to 10 power 16, sorry, 18, I think, 18, for 18 ohm meter. Okay, so greater than 10 power 18, or we can say greater than 10 power 6, sorry, say greater than 10 power 6, we can say those are insulators. The range is nothing but 10 power 6 to 10 power 18, like that. Okay, these are the typical values. And if we know the resistivity, the conductivity is nothing but just reciprocal. Conductivity is nothing but just reciprocal. Okay, those values are maybe in case of conductors 10 power 7 order. Sometimes we are getting the questions based on which is a low resistivity material, which is the high resistivity conductor, like that. Let us discuss those values with some examples. Okay, here coming to the resistivity typical values at 20 degrees centigrade. For silver, it is 1.59 into 10 power minus 8, copper 1.68, and gold 2.4, that is aluminum is 2.65. 2.65. So that means you can say that which is low resistivity element, that is nothing but silver. So low resistivity conductor. So we can say that low resistivity element. Low resistivity element, very, very important, is nothing but silver. So silver has low resistivity. If the resistivity is low, automatically for given length of wire and area, resistance also less. As the resistance is less, it allows more current. So we can say that is the best conductor of electricity. That's why you can say silver is the best conductor of electricity. Coming to this low resistivity case, silver is very less. After that, copper. After that, gold, or gold. After that, aluminum. Okay, it is also very, 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 very important. Okay, so silver is the best conductor of electricity because of low resistivity. So silver having low resistivity, so for given volume, silver has less resistance, so it allows high current. So we can say silver is best conductor of electricity. Best conductor of electricity. Okay, and coming to high resistivity in conductors, high resistivity materials, it is also very, very important. Resistivity in conductors. The high resistivity in conductors is nothing but carbon. If they have not given carbon, that is a graphite. Graphite is the allotrope of the carbon. It is a very, very high resistivity in case of conductors. Okay, we know very well graphite has one free electron, so due to that one only, it allows the electricity. Okay, and after that, nichrome, very, very important. Nichrome, wait, nichrome. After that, constant, and it is alloy. It means alloys. alloys having high resistivity, manganese. Okay, manganese. So if they are asking the question low resistivity silver, if the silver is not there, go for copper. If the high resistivity carbon or graphite, if these are not there, go for nichrome like that. Then you will get the idea. Okay, and in case of conductors, the resistivity is 10 power minus 8 order. 10 power minus 8 order means and capacitance. Okay, let us discuss inductance and capacitance. First of all, coming to the inductance. Inductance. We know very well, inductance is denoted by the letter L. Okay, it is nothing but electromagnetic property. Electromagnetic property of matter. Property of matter. Okay, it is an electromagnetic property. It stores energy in electromagnetic form. It stores energy in the electromagnetic form. So that's why it is an electromagnetic property of the matter. Coming to the inductor, coming to device, inductor. This is the inductor is a storage element. It is a storage element. It stores energy in electromagnetic form. It is a storage element. Stores energy as I said earlier, stores energy in electromagnetic form. Due to this storage property, it opposes the sudden changes in current. It is a storage element, stores energy in the electromagnetic form, and it opposes the sudden changes in current. Okay, that means it does not allow the sudden changes in current. Let us understand this one in a simple manner. All of you try to understand. If we have the municipality water tap, okay, and we are taking the water into any one container or bucket. For example, if there is any changes in the input of the water, the output of water also changes now. All of you getting my point? If there is any changes in the input of the water, the output of the water from this tap also changes. The speed of this water is high, here also speed is high. Here speed is low, here also speed is low. Okay, now how this inductor does not allow the sudden changes or which opposes the sudden changes means this inductor will be act as like a tank. It is the inductor. It is act like a tank. We are taking the water first of all into this tank. Okay, and our output, that means we are taking the output from this tank. Okay, then if there is any suddenly changes, for example, suddenly water is increased, the input of the tap, then also we are getting same water from here now. If the input of water is less, that means the speed of water is less, but then also we are getting the same water from here. That means why we are getting the same water from here? Because we have already some storage of water in the tank. Here we have already some storage of water in the tank. So that's why if there is any suddenly changes in the input of water also, we are not getting the change in water. Why? Because if for example your speed is increases, it will store some amount of the water and it will give constant. If the water flow is very less, then it will give some water to the output, then we are getting the same amount of the water. Okay, I think we can you can understand this one. Okay, so that means here the storage elements are act like a tank, either inductor or capacitor. So due to this storage property, whenever there is a sudden changes in the current, only sudden changes, friends. For example, if the change is 1 hour, 2 hours like that, then the total stored water is completed. Then whatever there is a change in the input, output also changes. Okay, so that's why I said it opposes the sudden changes in the current. Okay, so let us understand as concept wise this one. Let us take what inductor. Inductor, this is the symbol of the inductor. That means if you twist a wire into a coil, it will become inductor. L. The current flowing through the inductor is, let us take I of t. Okay, and voltage across the inductor is, let us take V of t. Then this voltage across the inductor V is equal to L di by dt. L di by dt. Let us understand. For small time there is a change. For small time as current changes. For small time as current changes, small time tends to t tends to 0. Okay, so as t tends to 0, what is happening? Di by dt is tends to infinity. That means you can say the voltage is infinity. All of you getting my point? For a small time, if the current changes means for small time means it is 0. Anything I by 0 means infinity. So anything by infinity is also nothing but infinity only. So voltage is infinity. So that means if there is a current will changes in the through the inductor in a small time, we have to get infinite voltage. Okay, we will get infinite voltage, but infinite voltage is not possible in our real environment. We are not getting the infinite voltage. If you are not getting the infinite voltage, then here what are the elements are opposing that one? Only one element is there now. Only one element is there which is opposing that sudden changes. So that means current is not changing in the very small changes in the time. Okay, I think all of you getting. Once again, friends, once again, for a small time, if there is any current changes, as time tends to 0, total di by dt tends to infinity. That means voltage will becomes infinity. But it is not possible. Okay, we are not getting the infinite voltage. If you are not getting the infinite voltage means here what are the elements we have? Resistor, inductor, capacitor. Inductor is there. Okay, so that means this person is opposing that one. This person is opposing that sudden changes. That's why we are not getting the infinite voltage. Okay, so as per this equation also can understand that it opposes the sudden changes in the current. Opposes the sudden changes in the current. If the time is high, for example, t tends to some 5 seconds, 10 seconds, we are getting the value. We are getting the value. Then value means there is no opposition by this inductor. Okay, so from this I want to write again the formula. Voltage across the inductor is L di by dt. From this, if you want to find out the current, then V dt is equal to L into di 1 by L V dt is equal to di. If you integrate this one, you will get current I. Current I is equal to 1 by L integral V dt. Okay, if you integrate that one, then you will get integration of di will becomes I is equal to 1 by L integral V dt. So you got the current through the inductor. This is the current through the inductor. Okay, so this is the voltage across the inductor. This is the current through the inductor. Okay, so these two formulas are very important, friends. These two formulas are very important. Here one more important thing is that, for example, if we have a core having cross section area A, if you wound a coil on this, having n number of turns, and the length of this core is, let us take L, okay, length of the core is, let us take L, then inductance L is equal to mu n square A by L, mu n square A by L. Okay, that means the inductance is directly proportional to number of turns square. Okay, so if you take a given length of the core and area, if you wound with wire with more number of turns, then inductance will be very higher. Here mu is nothing but permeability. Mu is equal to mu naught into mu r. It is nothing but permeability. We know what is the permeability. It is the ability to permit the flux. Okay, it is the ability to permit the flux. We know very well mu naught value 4 pi into 10 power minus 7 units are Henry per meter. Units are very, very important, friends. Okay, and mu r is equal to 1 for air. That is the relative permeability. It don't have any units. Okay, it don't have any units. So this formula is very, very important. Inductance L is equal to mu n square A by L. And coming to it, I said already, it is a energy storage element. Now, what is the formula for energy stored in the inductor? Energy stored in inductor, is nothing but half L into I square. Very, very, very important, friends. Energy stored in inductor is nothing but half Li square. It stores in electromagnetic form. Once again, friends, about the inductor or inductance. Inductance is a property of the matter. Okay, electromagnetic property. Inductor is nothing but it is a device. It is a storage element. It stores energy in electromagnetic form, which opposes the sudden changes in the current. Whenever there is a sudden changes in the current, it opposes. Okay, it may not oppose the long changes. Okay, only it opposes in transient conditions. So V is equal to L di by dt. If the current changes in small duration, then voltage must be infinity, but it is not happening. Means here the person only one is there, that is inductor. That is inductor opposes the sudden changes in current. Okay, for example, let us try to understand in a general manner. If we have the person A, one person is there, B, one person is there, C, one person is there. Okay, A taken one knife. Okay, A taken one knife and he is trying to kill the C. He is trying to kill the C like this. Okay, but here he is in the final case, we can say A is not killed the C. If the A is not killed the C, if C is not opposing, only one person is there. Which is that person? B. B person is there. He is opposing to kill the C. Am I correct? Here only one person is there, that person is B, who is opposes the kill of C. So that means here also same like that. Here only one person is there, inductor, that opposes the sudden changes in current. That's why we are not getting the voltage as infinity. And here these are the formulas. Okay, these are the formulas. And inductor L is equal to mu n square A by L, and energy stored in inductor is half Li square. Okay, I think all of you got it. Now we are going to discuss capacitance. Here, before going to capacitance, I want to give some important questions on this one. Okay, so based on these two formulas, V is equal to L di by dt. This is the one formula, that is voltage across the inductor, and current through the inductor is nothing but 1 by L integral V dt. In some cases, they will give the questions in the examination. If the current waveform is, let us take, they may give as square square, then what is the voltage waveform? What is the voltage waveform you will get if it flow through the inductor? Okay, or if they will give voltage across the inductor, voltage across the inductor is a step, then what is the current waveform you will get? Like that you will get the questions. Okay, like you will get the questions. If it is the inductor, if it is the VL, it is the IL. Okay, so then what we can say that here we have the one differentiation. For example, if you differentiate the parabola, you are getting square. You are getting, I mean, just wait. You are getting RAM. Differentiate parabola. You are getting RAM. We can also say that triangular shape. Triangle. Okay. If you differentiate this RAM or triangle, you will get step. Step, we can also say that square. Okay. If you differentiate this step, you will get impulse. You will get impulse. That means differentiation is reduces parabola, square relation, ramp directly proportional to x. That is nothing but here differentiation of step. Differentiation of step, that is just impulse. We know very well this is the impulse. Okay, this is the impulse. If it is 0, it is the waveform will be upon this y-axis only. Okay, the step or square. This is the step or square. Okay, and here ramp. Ramp is like this, a triangle. That means you can say linear. Okay, so linear means if you differentiate this x, then you will get a step that is nothing but like 1. Okay, so that is a constant value. So like that you are getting. So if they have given current is a square, voltage is differentiation of the current. Differentiation of the current. So VL is nothing but differentiation of this square. Differentiation of square means that is differentiation of step. Square means step. Differentiation of step, you are getting impulse. So we have to give the answer as impulse is the answer. Impulse is the answer. Here in the same way, the integration is increasing manner. Increasing manner means just opposite. If you integrate impulse, opposite friends. If you integrate the impulse, you are getting step or square. Step or square. If you integrate the step, you will get a ramp or triangle. Ramp or triangle. So if you integrate ramp, then you are getting parabola. Parabola. Okay, then what is the answer here? The current. The answer here is nothing but if you integrate the step, you are getting ramp. Current response is nothing but ramp waveform you are getting. Here you are getting impulse. Okay, like this we are getting the answers. These are very important for your JE and A exams, friends. Okay, just simply they will give if the device is an inductor. Okay, current flowing through that inductor is square, or current flowing through the inductor is ramp, or current flowing through the inductor is parabola. Then what is the voltage across it? Voltage waveform across it. Okay, just voltage is equal to differentiation of the current. Na? Differentiation of the current. So we have to differentiate that waveform, then we will get. Okay, same like here also. If they have given voltage, then you can easily find out the current. Okay, easily find out the current. In case of inductance, we have discussed that inductance is the electromagnetic property of the matter. Here in the same way, capacitance is electrostatic. That means charge, static charge, electrostatic property of matter. property of matter. Okay, coming to a device, capacitor. If you displace two charged plates, it is one charged plate, it is another charged plate. If you displace two charged plates with a distance d, or the distance d by air or through any one medium, any one dielectric, then capacitance will be formed. Then current through the capacitance is nothing but, let us take IC. If you apply the voltage across this, is nothing but VC. Okay, so current through the capacitance IC, voltage across the capacitance is VC. Once again friends, how the capacitor will be formed? If you displace two charged plates with a distance d by air or any dielectric, then capacitance will be formed. Okay, so this capacitance is directly proportional to area of the plates and inversely proportional to distance of the separation. So we can say C proportional to A by D. And if you remove the proportionality constant, we have to take one constant, that is epsilon A by D. So from this one, we can say that the capacitance depends on epsilon, dielectric. So capacitance value depends on, very very important point, depends on first one, nature of dielectric. That means nature of dielectric means either air, mica, paper. It means what type of dielectric you are using. And the second one depends upon area of the plates. And the third one, D. D is nothing but separation between the plates or distance between the plates. Separation between plates. Okay, so that means you can understand that here C is inversely proportional to D now. As D is higher, the capacitance is lower. That means if you displace with a very long distance, the capacitance is very less. If you displace with a very less distance, the capacitance is more. And don't think that, sir, if the displacement or if the distance or separation is zero, then the capacitance is going to be infinity. No, if there is no separation between these two, then that will be a conductor now. If it is one plate, it is another plate also is same connected like this, then it will becomes like a conductor only. Okay, so don't think like that. If at least there is some separation, then only the capacitance will be formed. I think so many students having doubt on this. Okay, so don't think that as the distance is zero, capacitance is infinity. Okay, so as the distance is zero, it is not belongs to a capacitor. It may not having the capacitance. It may not having the storage property. Okay, so capacitance depends on nature of dielectric, area of the plates, and separation between the plates, but not depends on thickness of the plates. Very very important question. Thickness of the plates. Okay, it may not depends upon the thickness of the plates. And coming to this epsilon is nothing but dielectric or permittivity. Epsilon is nothing but dielectric or permittivity. Let us discuss about that. If C is equal to epsilon A by D, epsilon is nature of dielectric or permittivity. Epsilon is equal to epsilon naught into epsilon R. Epsilon naught is equal to 8.85 into 10 power minus 12 farad per meter. Farad per meter is the unit of permittivity. Okay, farad per meter is the unit of permittivity. And epsilon R is equal to 1. Okay, And coming to the capacitor, this capacitor is a storage element. Capacitor is also a storage element. Storage element stores energy in electrostatic form. Stores energy in electrostatic form, that means charge, electrostatic form, and it opposes sudden changes in voltage. Sudden changes in voltage. As we have discussed in case of inductor, inductor opposes sudden changes in current, but capacitor is a voltage phenomena, inductor is a current phenomena. Once again friends, inductor is a current phenomena, capacitor is a voltage phenomena. It opposes the sudden changes in voltage. Okay, so let us understand this one. It is also same we can understand by tank principle. Okay, in the previous session I have given the tank principle in inductor. Same here also. If you have not watched that video, please click on the playlist and watch that one. Okay, and students, you can also download the electrical engineering classes PDF. Okay, for that you have to visit www.suneelengineeringacademy.com. In that you can get all the PDF of electrical engineering. Okay, so here if you can consider the capacitor, current through the capacitor is IC, voltage across the capacitor is VC. Here the formula is nothing but the current through the capacitance IC is equal to C dV by dt. C dV by dt. Okay, C dV by dt. For example, here also if the time is very low, at very less time, if the voltage changes, then what is happening? Dv by dt belongs to some change in value by 0, that is infinity. But infinity, that means I tends to infinity, but it is not happening. Not happen or not possible. Okay, infinite current is not possible now. Here it is not possible means because of only one person is here. Because of capacitance. That means we can say here capacitance does not allow sudden changes in voltage. Changes in voltage. I think all of you clear now. Like the same in the previous. Okay. So capacitance does not allow the sudden changes in voltage. And now coming to one more thing, we have the relation between voltage, capacitance and charge. That means charge through the capacitor or charge stored in the capacitor is nothing but charge Q is equal to, it depends upon that capacitance value and that voltage value. If you apply more voltage, then more charge. If you take more capacitance value of the capacitor, then charge will be higher. Q is equal to CV. It is the relation between these three. It is also very, very, very important, friends. Very, very important. And coming to the energy stored in capacitor, energy stored in inductor of Li square. Here, energy stored in capacitor is nothing but EC, that is of CV square. Okay, and in the previous I have given the waveforms, how we are getting, if they have given voltage or current waveform, how we are getting the remaining. Okay, so let us take that one. It is the IC, it is the voltage across C. Okay, so here what is the formula we have? I is equal to C dV by dt. If you want V is equal to 1 by C integral I dt. These are the two formulas now. So if you take a V here and if you integrate, then you will get 1 by C integral I dt. So for example, if they have given voltage waveform is a ramp. Then what is the current waveform? If they are asking like this, so current I is equal to C into dV by dt na. So that means if you integrate the voltage waveform ramp, if you integrate the if you differentiate the ramp, what you will get? Step na. In the previous session I have given. In the previous session I have given. So all this differentiation of ramp, that is step, differentiation of step, impulse, differentiation of parabola ramp, and integrations also I have given. Okay, you can also watch in the previous. So differentiation of ramp is nothing but step. Okay, so here the answer of the current is nothing but you can say step. Like in the same way they have given the question like if the current waveform is step, then what is the voltage waveform? Then voltage is equal to 1 by C integral I dt. Integration of step is nothing but you can say ramp. Opposite. Okay, so you can say ramp. Like that we can get the answers. We can get the answer. Once again friends, about this capacitance. Capacitance is electrostatic property of the matter, and here if you displace two charged plates in the medium of air or any dielectric with a distance of d or separation of d, then capacitance will be formed. That will be C is equal to epsilon A by d. If it will be depends upon nature of dielectric, area of the plate, separation between the plates, but not depends upon the thickness of the plates. It is a very important one. And here capacitance C is equal to epsilon A by d. Here epsilon is a permittivity, epsilon naught into epsilon r. These values are also very important, and these equations are very important. Note down this equation. And capacitance does not allow the sudden changes in voltage because of its stored property. And Q is equal to C into V, and here we have discussed the energy stored in the capacitor. Okay, and if they have given any voltage waveform and we can any waveform, and we can find out the another